So I'm gonna talk today about a topic that I call optimizing non-differentiable metrics, which is kind of a development that has happened in the last 2 to 3 years in the machine learning community. And then afterwards, I will gonna talk about how we use this kind of idea in autonomous driving. This whole thing is based on these kind of two papers. The left one is a book that I wrote on reinforcement learning. It's a tutorial that explains reinforcement learning from the perspective of non-differentiable optimization. And the other one is the recent arXiv draft where we are using kind of these ideas in autonomous driving. Now, you all know GPT-3, and when it came out back in 2020, this was a huge deal in the machine learning community, but it was generally not used much by the general public yet because GPT-3 was optimized with supervised learning, and GPT-3 was just repeating internet kind of style texts that were not very useful. And there were also like harmful texts coming out of this and so on. And kind of what made GPT into this product that now everybody's using into ChatGPT was something called reinforcement learning with human feedback, in which the AI model is trained via reinforcement learning to optimize a non-differentiable metrics, which is human feedback. So what is being optimized here is basically thumbs down or thumbs up. And so kind of through that, you can steer this model into predicting not just correct outputs, but useful outputs. Now, this is not the only development that has used this idea. There are several papers from DeepMind in Nature and so on. For example, on the top one, they have used a coding agent that they've trained with reinforcement learning to optimize the speed of the code. So they optimize the seconds the code uses to achieve the same results. And using that, they kind of have discovered a faster sorting algorithm. And there's a bunch of others. Also happened in computer vision. So in computer vision, we have these non-differentiable metrics like MAP or so. And if you actually optimize your neural network to maximize MAP instead of something else, you get better MAP. So kind of the main idea behind this is that in standard supervised learning, we kind of optimize sometimes things that we do not actually care about. Now, what do we actually care about? Well, we're PhD students, we want bold metrics in our papers, we want good results, right? I'm using metric in here in the colloquial sense. I'm talking about measures, but we call them metrics. Kind of, if you think about what is a metric, it's kind of a function that maps a input and a model prediction to a real number. Now, why can we optimize this with reinforcement learning? It's because reward functions are the same. They map a state, an input to the model, and a prediction, an action, to a real number. Now, so give you an understanding how this actually works in practice, I'm going to use a very simple classification problem. In classification, we want to maximize accuracy of our model, but accuracy is not differentiable. The 0-1 loss is not differentiable. So we use some surrogate losses. Now, if you wanted to do this reinforcement learning, what you typically do is, I'm using a technique called policy gradients here, is you write down the performance of your policy pi, of your neural network. And this is kind of, you can define this as the average over your data set, you have your samples, you have your kind of label predictions, then you can compute the reward for these samples and labels, and then you multiply that with the probability that your policy would have taken that action in that state. And the way we kind of maximize this or optimize this neural network now is we just take the gradient from the performance. So we take the gradient of the performance of our network with respect to the policy parameters. And now, because we are in classification and this is a single step environment, so there's one image, you make one decision, that's it. This is actually extremely simple. You just move it in. So basically, you just take this gradient. It's not dependent on the reward function. You just take the gradient of a policy. If in more general reinforcement learning, this is a famous theorem, but here it's basically trivial. Okay, so I said we want to optimize accuracy. So let's replace the reward function with the accuracy function. This is basically, it maps for a given image and a given class. It either maps it to 0 or 1. So 1 for the correct class and 0 for the wrong class. Because all the wrong classes are 0, you can remove them from the equation. So you can simplify the equation. And now we're basically only maximizing the gradient of the probability of the correct action. And now, by now, this kind of term might start looking familiar to you. What we now have to do to kind of move this back to the concepts that you're familiar with is we're optimizing log probabilities here, and you usually want to optimize log probabilities because it's more numerically stable. Now, if you actually optimize the log probability instead, so the log probability of the correct class, what you end up with is something called the cross entropy loss. You can also tell it negative log likelihood. So the reason why classification works so incredibly well is because cross entropy is actually maximizing accuracy, at least in the global optimum. Now, I've kind of given you now a different derivation of cross entropy from the perspective of reinforcement learning. But you might say, okay, that's kind of boring. I already knew that. So how's this useful for you? Well, imagine you're at your next job interview and the person's asking you, do you have any RL experience? Well, I'm using it all the time, right? Okay, but more serious, how do we actually use this in autonomous driving? The concept is the same. We take our driving metric and we turn it into a reward, and then we use reinforcement learning to maximize our driving metric. So in my field, we have this driving metric called driving score. It consists of a route completion and a penalty factor. So we drive along routes, we measure how far the progress is of the car, and then we penalize it every time it makes a mistake. We can turn this more or less, there's some technical details here, but more or less similarly into a reward function. We maximize route completion and we penalize, like we reduce route completion every time a mistake was made, and we add some terminal penalty and so on. The nice thing that has, so the one advantage is that we're going to get higher driving score if we optimize it, but the other advantage that we have seen with this particular reward is this also happens to scale much better than classical reward shaping. So what you typically do in autonomous driving is you define a lot of different individual rewards, you sum them up, a reward for center of the lane, a reward for don't crash, a reward for making progress, and so on. And what we kind of observed is that when you scale these up with larger mini batch sizes in an algorithm called proximal policy optimization, they start ending up in local minima. But kind of because this particular metric is also, it doesn't penalize trying because route completion always increases. It actually scales if you increase the batch size even further. And because the proximal policy optimization is a algorithm that scales well with batch size, basically the higher batch size you have, the more data you can use and the better your policy becomes. So overall, we kind of observed a huge performance improvement by using this technique. It is also the first time we beat supervised learning with reinforcement learning in this planning project. So kind of to give you an idea, the neural networks get these bird's eye view semantic renderings at input. This is kind of a privileged setting here. The simulator looks actually how it's depicted in the middle. And then it kind of steers the car using that privileged perception. And kind of what we observed is that we get very kind of good numbers compared to like recent state-of-the-art imitation learning models or diffusion planners or so on. The other nice thing that we observe is, for whatever reason, reinforcement learning methods seem to be able to train smaller models. So they've used an extremely small 2 million parameter model here, and essentially achieved better performance using 10 times smaller inference compute. Okay, so to end this talk, I think I want you to think about if you have an unusual metric in your problem that you're working on yourself, and whether you maybe should optimize that using reinforcement learning. Thank you.